Hello everyone, I am Deepa, faculty at Silver Hills Public School, Department of Mathematics. In this session, I will be discussing a topic from class 12 mathematics, and the topic is relations and functions. Now this topic is not new to you because we have already discussed the definition of relation, definition of function, and the difference between relations and functions in class 11, and that was our second chapter in class 11. In this session, we will be discussing different types of relations and questions based on it, and also a very small topic, that is equivalence class. So let us move to our topic, relations and functions. Let us recall some of the definitions which we discussed in class 11. The first definition is Cartesian product. And what is a Cartesian product? Suppose you have two sets A and B. The Cartesian product of A and B is denoted by A cross B. And what is A cross B? The set of all ordered pair AB such that where does this A comes from? A, that means the first member in the ordered pair comes from the first set, and B, that is the second member in the ordered pair comes from the second set B. So the collection of all these pairs together forms the Cartesian product of A and B. And how do we denote that? A cross B. Now I have given one example here. Consider set A equal to set 1, 2, 3, and you have another set, say B equal to set 2, 3. So how do you find the Cartesian product of A and B, children? A cross B is equal to, just fix the first set. Okay, that is A. How many members are there? 3 members, 1, 2 and 3. So we start with 1. 1 is paired with 2, 1, 3, okay, 1, 2, 1, 3. Then comes 2, 2, 2, 3, 3, 2, 3, 3. So these are the members of the Cartesian product of A and B, and we denote it as A cross B. And you know this, what is A cross B? After that, we discuss relation, the definition of relation. What is the definition of relation? A relation R from a non-empty set A to another set, say B. Another non-empty set B is always a subset of the Cartesian product of A and B. That is, a relation from A to B is always a subset of A cross B. And then if a pair belong to our relation R, we would say A is related to B. That means there is a connection between A and B. And how do we write? We write A R B. That is, how do we read that? A is related to B. So let us discuss one example. Okay. So now children, relation, what is the meaning of that? In our daily life, we come across different types of relation, isn't it? What are the different relations? Say, relation between brother and sister, mother and father, husband and wife, and so many relations are there in our daily life. So in mathematics also, suppose you have two sets, A and B, which is non-empty. Non-empty means some members are there in both the set. So I can connect the members of one set with the members of another set using some connection. That is called a relation. So let us do one example and let us check what will be the answer for that relation. So let us do it. Let us consider a set A equal to set 1, 2, 3, and another set B is equal to set 2, 3. So we all know how to write the Cartesian product of A and B, because the same question I showed you in the definition of the Cartesian product. So what is A cross B? The Cartesian product of A and B is equal to, I will just pair the members of A with the members of B. So I get 1, 2, 1 3, 2 2, 2 3, 3 2, 3 3. These are the members of A cross B. If I consider each member from the ordered pair, the first member of each ordered pair comes from the first set and the second member of each ordered pair comes from the second set. Now I am going to connect the members of the first set with the members of the second set by some relation. So let me define a relation R from A to B as, say, R is equal to set of all ordered pair XY such that X is less than Y. This is my relation. What is it? I want those ordered pairs satisfying this condition. This X denotes the first member of the ordered pair and Y denotes the second member of the ordered pair. So I need those pairs such that the first member is less than the second member. So I have the entire members of A cross B here. It's listed. So let me see which all members I can include in this collection. Can I include 1, 2? Yes, I can. Why? Because 1 is less than 2. So I am going to include 1, 2 here. 1, 3. Can I include 1, 3? Here X is 1, Y is 3. 1 is less than 3. I can include that. 2, 2 I cannot include because 2 is equal to 2. I can't say 2 is less than 2. What about the next one? 2, 3. Yes, I can include 2, 3. 3, 2. No. 3, 3 also I cannot include 3, 3 in our collection. So I just close this set notation. So these are the members of R. There is a connection between each member. So if I take an ordered pair, there is a connection between the first number and the second number. Here also there is a connection and the third one also there is a connection. And what is a common connection, common relation? First member is less than the second member if we take each ordered pair. Not only that, consider R. All the members in R, they are present in A cross B. See, 1, 2 is present, 1, 3 is present, 2, 3 is present there. So that is why we define a relation from a non-empty set A to a non-empty set B. It is always a subset of A cross B. It is always a subset of the Cartesian product of A and B if it is from A to B. Okay. So if the first set and the second set are same, say A, then I would say a relation on A. So that means that the relation is from A to A. Hope that is clear to you. So now let's discuss different types of relation. So definition is clear to you. So now let's move to the different types of relation. I'll give you one example, then we'll move to the definition. Let's consider a set. What is our set? Say A is equal to set of all students of a boys' school. So that is my set of all students of a boys' school. And I am going to define a relation on this set. On this set means the members are all students from a boys' school. So my relation R is equal to set of all ordered pair XY such that X is the sister of Y. What is it? What's my relation? I need those pairs satisfying this relation. What is the relation? X is the sister of Y. So if I include a pair, the first member should be the sister of the second member. So how many members will come in this relation R? Can I include any members here? What is our set? The collection of all students of a boys' school. So boys school means all the students will be boys, and here the relation is sister of. So the word sister is associated to girls, right? So I cannot include a single member in this relation. So what do I conclude? My relation, the members are absent, or my relation is empty. So I would write R is equal to 5. So such a relation where there are no members inside the relation is called an empty relation, and that is a first type of relation, that is empty relation. Empty relation. A relation which is empty, that is called empty relation. So now let us define another relation which is just the opposite of empty relation. Let us see what it is. I am going to change the set. So let me take A is equal to, say, set of all students of a school. And then I am going to define a relation on this set. So let the relation be, say, R is equal to set of all ordered pair XY such that the difference between the age of X and Y is less than 50. So what is my relation? If I take a pair, the difference between the age of those two students, it should be less than 50. Okay, that must be less than 50, that is a relation. So coming to our set of all students of a school. So let us take this school, set of all students of Silverville School. So here we have students right from KG to 12th standard. Now if I consider a student who is studying in KG, what will be the age of that child? Maybe 5, okay, 5 or 4, we will take 5. And then I am considering a student who is in class 12. So what will be his age? So let us take it as 18, 18 or 17, we will take it as 18. So what is the difference between the age? You have 18 minus 5, that is 13, and 13 is a number which is less than 50, isn't it? So like that, if you take any two students studying in the school, maybe any class, when you find the difference between their age, the difference will be less than 50. It will never exceed the value 50. That is why I took the two extreme cases, a student who is in KG class and one who is studying in class 12. So just imagine the two students whom you selected, they are studying in the same class, say class 12. So the age will be, say, 18, both will be 18 or 18, 17, that can also happen. So if it is 18, what is 18 minus 18? 0, still that is a number which is less than 50, no problem. And then again, if you find the difference 18 and 17, 18 minus 17, that is 1. Okay, so whatever it is, the difference of the age will not exceed 50. So how many members will come inside this R? How many members will come? We know what is the definition of a relation. It is a subset of, say, A cross A if it is from A to A. Here the relation is from A to A itself. So I can include all the members of the Cartesian product of A, that is A cross A. I can include all members of A cross A. So in other words, R is equal to A cross A. Such a relation which has all the members of A cross A is called a universal relation. What is it? Universal relation. The first relation was empty relation. The second one is universal relation, just the opposite of which relation? Empty relation. Hope these two are clear to you. Now empty relation and universal relation, they have a name. We call them trivial relation. Why we say trivial relation? Because empty relation, we know the members are absent. A relation which is empty is called empty relation, and a relation which has all the members of the Cartesian product is called a universal relation, and this does not need further explanation. So that is why we call they are trivial relations. Okay? So now let us go to the definition of these two, which we already discussed. The types of relation, the first one is empty relation. So how do we define that? A relation in A is said to be an empty relation if no element of A is related to any element of A. That means there is no connection between the members. And R is equal to phi, which is of course a subset of A cross A. And what is the next one? Universal relation. A relation R in a set A is called universal relation if each element of A is related to every element of A. So what is R here? R is equal to A cross A. Hope that is clear. So now let us discuss another set of relations. We have three relations here. So what is written here? A relation R in a set A is called reflexive if, what is written? A comma A, ordered pair AA belong to R. Here R means relation for every A member of the set A. So what is the first one? Reflexive. I will just explain to you what each one is, and then I will take a problem. So if we discuss a problem, it will be clear to you what the meaning of each definition is. Reflexive relation R in a set A is called reflexive if A comma A belong to R. Second one, symmetric. What is that? If you take ordered pair AB, ordered pair AB means the first member and second member, they are different. If you take ordered pair AB, it is reverse thing, that is ordered pair BA will be present in the relation. Then I will say that relation is symmetric. So the first one is reflexive, meaning every element is paired to itself. A comma A belong to R. Second one is symmetric. If a different pair, if AB belong to R, then BA will be present in the relation. Now the third one is called transitive. And what is transitive? There we need to consider two pairs. If AB is present in the relation and BC is present in the relation. So the important thing that you must note is, here it is AB, second element is B. So we must select a pair in such a way that the first element of the pair, that will be B. So I have selected BC. So if AB and BC is present in the relation, then the first and the last, that is AC will be present in R. So if a relation satisfies this condition, that is called a transitive relation. Reflexive, symmetric and transitive. So let us take one example and let us check in each case whether the given relation is reflexive, symmetric or transitive. Now one more thing, suppose you have a relation satisfying all these three conditions, that is you have a relation which is reflexive, which is symmetric and transitive. Then that relation has a name, we call it as an equivalence relation. What is it? Equivalence relation. A relation in a set A is said to be an equivalence relation if it is reflexive, symmetric and transitive. So if all these three properties holds, that relation is said to be an equivalence relation. Okay? So now let us consider an example. Look at this, I have listed 5 relations here and that too in which form? Roster form. So, it is easy for you to check the property whether it is reflexive, symmetric or transitive. So, let us read the question. You have A equal to the set is set 1, 2, 3. Check whether the following relations defined on A is reflexive, symmetric or transitive. So, we need to take each question and let us check whether it is reflexive, symmetric or transitive. So, just take the first one. R is equal to 1, 2, 2, 1, 2 members are there. So, just go back to the definition of reflexive. What does reflexive property says? The reflexive property says if you have a relation defined on A, then A will be present in the relation for all A element of the set. So, now in this question, A has 3 members 1, 2 and 3. So, we are going to check whether 1, 1 is present, 2, 2 is present and 3, 3 is present in this question, in this relation. No, 1, 1 itself is not present, so we need not check the remaining thing. So, what do we conclude? We conclude this relation is not reflexive. Okay? Second one, we will check whether this relation is symmetric. So, what is the definition of symmetric? A relation is said to be symmetric if AB belong to R implies BA belong to R. Look at this, I have an AB, the first member and the second member are different 1, 2. So, just check whether 2, 1 is present in the question. Yes, 2, 1 is present. So, I can conclude the given relation is symmetric. Then comes the transitive property. Is this relation transitive? So, what was the definition? If AB and BC. So, I selected AB 1, 2. Okay. So, and then I have a pair that is starting with 2, 2, 1. If so, the first and the last member, these two, that is ordered pair 1, 1, that must be present in this relation. So, is 1, 1 present here? No, 1, 1 is absent. So, we will conclude this relation is not transitive. This relation is not reflexive, but this relation is symmetric. So, I will write S. What does this S denote? This relation satisfies only the symmetric property. It is not reflexive, it is not transitive. Second one, R is equal to 1, 1, 2, 2, 3, 3, 1, 2. So, first property reflexive. We will check whether 1, 1 is present. Yes. 2, 2 is present. 3, 3 is also present. So, it is definitely reflexive. Second property, whether it is symmetric. So, what to do? Just check whether a pair AB is present, where the first element and the second element are different. So, here the first member and the second member are same, but we have an order pair 1, 2 present there. So, 1, 2 is present. So, is 2, 1 present here? No. So, we will conclude the relation is not symmetric. It is reflexive, but it is not symmetric. And what is the third one? The third one is transitive. And definition, remember the definition. If AB and BC is present, then AC will be there in the relation. So, I will select 1, 2. My A is 1, B is 2. So, naturally I will go for a pair that starts with 2. So, here in this relation it is 2, 2, isn't it? So, I have 1, 2 and I have 2, 2. So, if I combine these two, I get 1, 2, isn't it? Yes, 1, 2 is present there. So, I would conclude the given relation is transitive. So, which all letters I can use here? It is reflexive. Okay. R stands for reflexive. Is it symmetric? No, but it is transitive. Okay. So, the first one is just symmetric, second one it is reflexive and transitive. Coming to the third one, we will check whether the given relation is reflexive. 1, 1, 2, 2, 3, 3, yes. So, it is reflexive. So, I will just write R. R shows it is reflexive. What about the symmetric property? I have 1, 2, AB is present. Is 2, 1 present here? Just check whether 2, 1 is present here. No, 2, 1 is absent. So, I can conclude the given relation is it is not symmetric. Then comes the third one, that is transitive. AB and BC. If AB and BC is present, then AC will be present in the relation. So, look at this 1, 2. And I have a pair that starts with 2. So, what about if you combine the first and the last? It is 1, 3. Is 1, 3 available here? No, 1, 3 is not there. So, what does that mean? The given relation is, it is not transitive. So, it is only reflexive, neither symmetric nor transitive. Coming to the fourth one. We are searching for 1, 1. Yes, 2, 2. What about 3, 3? 3, 3 is absent. Okay? So, it is not reflexive. For a relation to be reflexive, A must be present in the relation for all A member of the original set. So, how many elements are there? 1, 2, 3. 3 members are there, but here we have just 1, 1 and 2, 2, 3, 3 is absent. So, it is not reflexive. What about the symmetric condition? I have 1, 2. Now, 2, 1 is present there. Okay. So, it is symmetric. So, I can write S. S denote the given relation is symmetric. Then comes the transitive condition. We are going for AB. Choose AB and BC and just show if AC is present, it is transitive, or else we will conclude it is not transitive. Look at this 1, 2. And you have a pair starting with 2, 2, 1. So, what about 1, 1? Yes, you have 1, 1 here. Okay. So, now if you take 2, 1, you have 1, 1. 2, 1 is present. Yeah. So, I can conclude the given relation is transitive. So, it is symmetric as well as transitive. Last question. 1, 1 present, 2, 2 present, 3, 3 present. So, without any doubt I can say the given relation is reflexive. Coming to the symmetric, 1, 2 is present, yeah 2, 1 that is also present there. So, it is symmetric. Third condition is we check whether it is transitive. So, 1, 2 is present, 2, 1 is present. So, what about 1, 1? Yes, 1, 1 is present in the question. So, I can conclude the given relation is transitive. So, I can write reflexive, symmetric, transitive. All these three properties holds here. And what is the name of such a relation? A relation which is reflexive, symmetric and transitive is called an equivalence relation. So, our last example is an example for equivalence relation. Okay. And then some of you will have a tendency to write symmetric instead of reflexive, reflexive instead of symmetric. Okay. So, maintain the order. The first one is reflexive. So, children, like reflexive means reflection. See, suppose I have a mirror with me. If I look into that mirror, I can see myself, isn't it? So, this person and this person both are same. So, in that sense, keep some clue in your mind. So, reflexive means ordered pair AA belong to the given relation. Second one is symmetric. Symmetric means the first member and the second member. If it is ordered pair AB, then BA, the reverse thing, ordered pair BA will be present in the relation. Okay. And only for the third one, that is transitive, we are considering two ordered pairs, such a way that if I take the first one as AB, the second one will be BC. Okay, you are ending with B and the second pair starts with B, that is very important. And if AC is present in the question, we will conclude that relation is transitive. Suppose we are not able to select a pair, say AB and BC. Such a pair does not exist. So, what do we conclude? Do not conclude that it is not transitive, because we did not prove anything. We did not prove that AB and BC is present, AC is absent or AC is present. We did not prove anything. In such case, we will conclude that relation is transitive, and we will do examples, do not worry. Okay. So, now this relation, all these relations are in roster form. So, let us take one example where you have the set builder representation of the relation. So, what is this? Let T be the set of all triangles in a plane, with relation and R is a relation in the set of triangles given by, what is a relation? If you take two triangles, the first triangle will be congruent to second triangle. So, what is it? T1, T2. If T1, T2 is a member of R, T1 is congruent to T2. That is a relation. If you take any two triangles, those two triangles will be congruent. Show that R is an equivalence relation. It is said, show that R is an equivalence relation. That means we know that will be reflexive, it will be symmetric and transitive. We just have to prove it. So, let us see how to write the proof. We go in order. The first one is reflexive. Okay, reflexive. Let T1 belong to T. That means I took a triangle T1 and this triangle comes from the set of all triangles which is denoted by T. I can always say a triangle is congruent to itself. That result is true. Every triangle is congruent to itself. So, I can say T1 belong to R. What does that mean? T1 is congruent to T1. Every triangle is congruent to itself. So, I can say this relation is reflexive. Second property is symmetric. When you prove the symmetric property, always consider a pair. In our definition, it was say ordered pair AB. A and B are two different elements. Here we are dealing with set of all triangles. So, I will just consider let T1, T2 belong to R. There is a member in the relation. What is the meaning of this? This implies T1, the first triangle is congruent. I am using the symbol of congruency. I say T1 is congruent to T2. So, if I draw two triangles ABC, say PQR, and if I name it as T1, if I name it as T2, T1 and T2, I say T1 is congruent to T2. That is what I wrote here. This is same as I can also say T2, first one is congruent to second one. So, second one is also congruent to first one, that is also true. So, I am writing it as T2 is congruent to T1. What does that mean? If T1 is congruent to T2, then T1, T2 belong to R. See here, I got T2 is congruent to T1. What does that mean? T2, T1 belong to R. So, our definition AB belong to R implies BA belong to R. So, the given relation is symmetric. It is reflexive, it is symmetric. So, we need to prove transitive condition, we need to prove the relation is transitive so that the entire relation becomes an equivalence relation. So, how to prove the transitive property? For that, we need to consider how many pairs? Two pairs. So, let T1, T2 belong to R, and when we consider the next pair, remember that pair it must start with T2 and T2 comma some T3 belong to R. So, I selected the pairs. Now I write the meaning of each thing. T1, T2 belong to the relation. What does that mean? This implies T1, triangle 1 is congruent to triangle 2, and you have T2, T3. So T2, triangle 2 is congruent to the third triangle T3. Okay, so you have a triangle which is congruent to another triangle, and that triangle is congruent to another one, say T3. What does that mean? This means T1, the first triangle is congruent to T3, T1 is congruent to T3. Let it be T1, T2, T3. T1 is congruent to T2. T2 is congruent to T3. That is same as what? You can say T1 is congruent to T3. That's true. So that's what I wrote here. T1 is congruent to T3. And what is the meaning of that? Which implies T1, T3 belong to a relation. So we proved this, the third property, that is transitive. Okay. So this was the transitive property. Reflexive, symmetric and transitive. So relation satisfying all these three is called equivalence relation, and here we proved it is an equivalence relation. And a question comes from this area, children. So concentrate more on this session where you get questions to prove whether the given relation is an equivalence relation or not. So we just have to prove these three conditions: reflexive, symmetric and transitive. Consider the second question. Let L be the set of all lines in a plane and R be the relation in L defined as, what is the relation? R is equal to set of all ordered pair L1, L2 such that L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. Okay, so the clue is also given in the question, we just have to prove it. What is given? Show this relation is symmetric. So you know the condition of symmetry, so just prove it is symmetric, but neither reflexive nor transitive. So what is our collection? What is a set? Set of all lines. And what is the, if you take two lines, what is the connection? What is the relation between those two lines? One line is perpendicular to the other line. So let's check the first condition. What is the first condition? Reflexive. So let's take, say, one line which comes from the collection of lines. Will we say a line is perpendicular to itself? Is it right to say a line is perpendicular to itself? That's wrong. But I can say a line is parallel to itself, but we don't say line is perpendicular to itself. That is wrong. So if I take a line in this collection, L1, comma L1 does not belong to our relation. Why? Because a line cannot be perpendicular to itself. A line is not perpendicular to itself. So L1, L1 will not come in the relation. What does that mean? That means this relation is perpendicular to, that is not reflexive. So not reflexive. And then it said, prove that it's neither reflexive, so we prove it's not reflexive. Now we'll move to the next property, and what is that? Symmetric. So to prove the symmetric property, we need a pair where the first member and the second member are different. So how to start? Let L1 L2 belong to R. They are related. What is the relation? L1 is perpendicular to L2. So, I just write the meaning of this, which shows L1 is a symbol perpendicular to L2. So, I have two lines, L1, the other one is L2. So, L1 is perpendicular to L2. Can I say the other way? Is L2 perpendicular to L1? That is also right. So, L1 is perpendicular to L2 is same as L2 perpendicular to L1. And what does that mean? If L1 is perpendicular to L2, I will write L1, L2 belong to R. Here I got L2 is perpendicular to L1. So, what does that mean? L2, L1 belong to R. So, what is this property? It is symmetric. So, definition, if AB belong to R, BA also belong to R. Just like that, L1, L2 belong to R, L2, L1 also belong to R. So, we proved it is symmetric. So, we proved this part. We proved it is not reflexive, and one more thing we need to prove, that it is not transitive. For that, how many pairs we need to consider? 2 pairs. Let L1, L2 belong to R and L2, some L3 belong to R. So, that is a connection. L1, L2 belong to R, L2, L3 belong to R. Now, we will write the meaning of these. What does this mean? This implies L1 is perpendicular to L2 and L2 is perpendicular to L3. Okay? L1 is perpendicular to L2 and L2 is perpendicular to L3. So, can we say L1 is perpendicular to L3? We will just draw the figure and check. I have L1, I have L2. These two are perpendicular. And then I have L2 which is perpendicular to L3. So, how can I draw L3? I can draw like this, isn't it? Here, this is my L3. L2 perpendicular to L3. So, what can you say about this line and this line? Are they perpendicular? No, but they are parallel. But our relation is the two lines are perpendicular. One line is perpendicular to the other line. So, from here this implies L1 is not perpendicular to L3. That is L1, L3 does not belong to our relation. That is not a member of R. So, we proved the given relation is not transitive. Okay? It is just symmetric. It is neither reflexive nor transitive. So, next example, see. Determine whether the relation R on n, what is this n? N stands for set of all natural numbers, defined by R is equal to set of all ordered pair xy such that y is equal to x plus 5 and x is less than 4 is reflexive, symmetric and transitive. Determine whether, so we need to check whether it is reflexive, symmetric or transitive. Now, the given question is in set builder form. So, for our convenience we will just convert this into roster form. So, when you write the roster form, how can you write the relation? R is equal to, I need those pairs such that the second number will be 5 greater than the first number and the condition is x should be less than 4. So, which is the first natural number? 1. So, the first value that x takes is 1. So, when x is 1, what is my y? 1 plus 5, that is 6. The first pair is ready. Next natural number is 2. So, when x is 2, my y is 7 because 2 plus 5 gives 7. Next x is 3. So, what is my y? 3 plus 5, that is 8. Can I include any other x? No, because condition is there, x is less than 4. So, I can select only 3 values for x, 1, 2 and 3. We will stop there. So, this is my relation in which form? Relation in roster form is ready. Now, let us see whether it satisfies all the 3 properties. What about reflexive? Is this relation reflexive? For that, remember A belong to R. So, which is the first element in the set? We are dealing with natural numbers. The first element is 1. Is 1 present? No. So, 1 itself is absent. So, we need not check the remaining. So, we conclude this relation, it is not reflexive. Okay, it is not reflexive. So, not reflexive. What about this property symmetric? Let AB belong to R. So, what is AB here? 1, 6. 1 and 6 different. So, I just took that pair. Is 6, 1 present somewhere here? No, 6, 1 is absent. So, we conclude this is not symmetric. So, not reflexive, not symmetric. Then comes a transitive. What is the definition? If AB and BC is present, then AC will be present in the given relation. So, 1, 6. Can you find another pair starting with 6? No. So, that means in this question, if I take any AB, I am not able to find some BC. Okay? I cannot prove whether it is transitive. To prove transitive condition, AB and BC must be present in the given relation. So, what will be our conclusion? We will conclude, we did not prove anything. So, we will conclude that the given relation is transitive. Okay? We are not concluding it is not transitive. We conclude the given relation is transitive. Okay? So, we prove this it is transitive. Because we did not prove that AC is absent. AB and BC is not there in the question. That is why we just conclude the given relation is transitive. Okay? Now, let us do one more problem in this area, that is equivalence relation, to prove whether a relation is equivalence or not. What is that? Show that the relation R in the set Z of integers given by R is equal to set of all ordered pair AB such that is if you include a pair, what is the relation? 2 divides A minus B. That means the difference between A and B, it is an even number. And we are going to prove that is an equivalence relation. That means it is reflexive, symmetric and transitive. So, let us write the first one. Reflexive. So, let us consider A. What is our set? Integers. So, I consider A element of Z. I can say A comma A belong to the given relation. I can say this. Why? Because look at this. Because 2 divides A minus A, isn't it? What is A minus A? 0. So, I can say 2 divides 0, no problem. In that sense, I will say A belong to the given relation for all A element of the original set. And which is the original set? The original set is set of all integers. So, the given relation is reflexive. So, the first property is done. Second one, symmetric. How do we start? Let AB belong to the relation. Once a pair is selected, we write the meaning of this. So, if AB is there in the relation, what does that mean? 2 divides A minus B, which implies 2 divides A minus B. If 2 divides A minus B, I can say 2 divides minus of A minus B, isn't it? I can say 2 divides 4. So, same way 2 divides minus 4 also. Same way I can say 2 divides minus of A minus B. And what is minus of A minus B? It's B minus A. This means 2 divides B minus A. What does that mean? B comma A belong to the given relation. So, we started with this AB belong to R implies BA belong to R. So, this is symmetric. Now, we just have to prove the given relation is transitive so that it is an equivalence relation. Now, let us prove whether the given relation, let us check whether the given relation is transitive. Now, it is given in the question it is an equivalent, prove it is an equivalence relation. So, we are going to prove this given relation is transitive. For that, we need to consider 2 pairs. Let AB belong to R and BC belong to R. Now, we are going to write the meaning of this. AB belong to R means 2 divides A minus B and 2 divides B minus C. Okay. So, we know 2 divides 4, 2 divides 6, that is 4 and 6 are 2 even numbers. So, what is 4 plus 6? 10. 2 divides 10, that is 2 divides sum of 2 even numbers. Okay. So, I have an even number here, another even number. So, 2 divides the sum of those two, which implies 2 divides A minus B plus B minus C. Now, minus B goes and we get 2 divides A minus C. And what does that mean? AC belong to the given relation. So, we proved this relation is transitive. So, it is reflexive, symmetric and transitive. So, this question, that is an equivalence relation. Hope all these questions are clear to you. Now, let us move to a different topic, that is called equivalence class. Equivalence class. What is the definition of an equivalence class? It is not equivalence relation, it is equivalence class. Let A be any set and R be an equivalence relation in A. So, you have a set A and you have a relation on that set. What kind of a relation? It is an equivalence relation, meaning a relation which is reflexive, symmetric and transitive. The equivalence class of an element A in A. So, if you take an element in your set, its equivalence class is denoted by, we use a square bracket to denote that, equivalence class A. And here is a definition of equivalence class A. What is equivalence class A? Set of all members in A, set of all x in A such that x is related to A. There is a relation between x and A. I need those elements in A which are related to this small a. That is a definition of equivalence class. I will just move to a question and from there you will get a clear idea of what an equivalence class is. Okay, so, we will just do one problem. Look at this. You have a set, let A equal to set 1, 2, 3 and R be the equivalence relation on A given by R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. Okay, these are the pairs and definitely this is an equivalence relation. It is given in the question, so we are not going to prove it. what is the next part? Find equivalence class 1, equivalence class 2 and equivalence class 3. Okay. So, let us equivalence class 1, we are going to find that. What was the definition of equivalence class A? Here it is, set of all x in A such that x is related to A. So, in the place of A we have 1 here. So, I would write equivalence class 1 is set of all elements, set of all x in A such that x is related to 1. That means, what does this show? This means a pair like this belong to R. That is the meaning. You need to select a pair which is present in the given relation and collect all x value, which gives you equivalence class 1. Now, look at R. Just check in which pair 1 occupies a second place. Here, isn't it? 1 occupies a second place. So, in the place of x I can include 1. So, I will write equivalence class is equal to set of all x in A. So, 1 such x I got, which is 1. Now, 2, 2, no, 1, 2. See here, in this pair 1 occupies a second place, and what is the x that is just before 1? It is 2. So, I got the next member. Okay. So, there are 2 members in equivalence class 1, that is set 1, 2. Now, we will write equivalence class 2, and what is that? Set of all x in A such that by definition x is related to 2. So, what does that mean? Ordered pair x2 belong to R. So, we are going to search for a pair where 2 occupies a second place and what is the x that comes just before 2. So, here this one 2 occupies a second place. So, what is the x just coming before 2? It is 2. So, I got 1 x. Then here I have 1 2. So, the member that is coming just before 2 is 1. So, set 2 1. Now, set 2 1 is same as set 1 2 because in roster form order is not so important. So, equivalence class 2 is also ready and we need to find equivalence class 3. So, equivalence class 3 is equal to set of all x in A such that x is related to 3. X is related to 3 means I need to select a pair like this. x3 belong to R. x3 belong to R. So, select a pair in which 3 occupies a second place and check what comes before 3. So, which is that? I have here 3 occupies a second place, and what is the number that comes before 3? It is 3. So, only one such pair x is here. So, I would write just a single element set 3. So, this set 1 2 represents equivalence class 1, set 1 2 represents equivalence class 2, set 3 represents equivalence class 3. Now, these equivalence classes has some properties. So, we will be discussing that. Okay. So, now let us summarize all these results. Our set was set 1 2 3. So, I will just rewrite it. My original set was set 1 2 3, and then I got the answer for equivalence class 1, equivalence class 2, equivalence class 3. What was equivalence class 1? I got the answer as 1 2. Let me name it as some A1. Okay, as set I just named it as A1, and equivalence class 2 also I got the same members. So, I will give A1, I will just name it as A1. Now, coming to equivalence class 3, you have just one member. So, I can give another name for that, A2. So, I have A1, A2. Based on this, I can list few properties of equivalence class. What is it? That is there here, it is here. Look at this note. The first note is corresponding to every element in A, there is an equivalence class. Do you agree with it? Let us go back to our question. This is my A. How many members were there? 3 members. So, equivalence class 1 is there, equivalence class 2 is there, equivalence class 3 is there. So, the first property is okay. Corresponding to every element in A, there is an equivalence class. What about the second one? Any two equivalence classes, they are either identical or disjoint. I will just take equivalence class 1 and equivalence class 2. What can you conclude? I can say those two are same. So, if I take any two equivalence classes, either they will be same or they will be disjoint. Disjoint means intersection is empty, elements are not common. So, now if I take equivalence class 1 and 3, what can you say? Members are entirely different, they are disjoint. So, hope that note is clear to you. Any two equivalent classes, they are either identical or disjoint. Last one, the collection of all equivalence classes forms a partition of our set A. So, what do you mean by a partition of a set? If you have so many subsets A1, A2, A3, we say those set form a partition of A if it satisfies two conditions. One is, if you find the union of all those subset, you get the original set. Not only that, if you take any two set, the intersection will be empty. Let us check it. Look at this. A1, A2, these are the subsets of A. What is A1 union A2? A1 union A2 is set 1, 2, 3, isn't it? Which is our original set A. Now, what is A1 intersection A2? A1 intersection A2 is, see this is A1. Is there anything common in those two? No, we will conclude it is 5. So, that means they form a partition of the original set. So, once again, corresponding to every element in A, there is an equivalence class. Second one, if you take any two equivalence classes, either they will be same or they will be disjoint. And finally, A1, A2, A3 are equivalence classes, they form a partition of our original class A. So, now let us do few questions based on equivalence class. Now, if the idea is clear, it is easy for you to find the equivalence classes. So, let us check the example here. Show that the relation R on the set A. So, what is our set A here? Set of all x in Z. Z denotes integers and x lies between 0 and 12. And the relation is given by set of all ordered pair AB such that modulus of A minus B is a multiple of 4 is an equivalence relation. Also find equivalence class 1. So, two questions are there. First of all, we need to prove that is an equivalence relation, which we know. And the second part says find equivalence class 1. So, we will do the first part, that is we are going to prove this relation is an equivalence relation. So, first one, reflexive. If I take an integer, say A in Z, let us see, I can conclude A belong to the relation R. Why? Because modulus of A minus A, that is equal to 0. So, I can say it is a multiple of 4. is a multiple of 4. So, I can conclude the given relation is reflexive because A comma A belong to the relation. So, first property is done. Next is symmetric. For that I need how many pairs? Just one pair where the first member and the second member are different. So, let A, B belong to the relation R. So, we will just write the meaning of it. What does that mean? Modulus of A minus B is a multiple of 4. So, I just write it as say some 4k, where k takes the values 1 to etc. Mod A minus B is equal to some 4k. If so, I can write mod B minus A is also some multiple of 4, because inside the modulus of a negative number comes when you take the modulus any way that is positive. So, mod A minus B is a multiple of 4 is same as mod B minus A is a multiple of 4. What does that imply? B comma A belong to the relation R. So, we started with this. AB in R implies BA in R. So, this relation is symmetric. Now, one more part, that is we will just prove it is transitive. So, how many pairs we are going to consider here? 2. Let AB and BC belong to R. So, let AB belong to R and BC belong to R. We just write the meaning of it, which implies modulus of A minus B is equal to, modulus A minus B is a multiple of 4. That means I can say mod A minus B is some 4k1. Okay, I am just using 4k1. Same way, this mod B minus C belong to R means mod B minus C. BC belong to R means mod B minus C is also a multiple of 4. So, I denote it using this. Mod B minus C is equal to 4k2. Now, this implies, so if I remove the modulus, the number inside the mode, it can be positive or negative. So, I can write A minus B is equal to some plus or minus 4k1 and B minus C, that is also some plus or minus 4k2. Okay. Which implies, what is our aim? Our aim is to get AC. We need to prove AC belong to the given relation. Now, I am going to add these two. So, A minus B plus B minus C, that is equal to plus or minus 4k1 plus or minus 4k2. Now, minus B and B get cancelled and I get A minus C. A minus C is equal to plus or minus 4, if I take the bracket, k1 plus k2 comes inside the bracket. Okay, that means A minus C is a multiple of 4, which I can write as mod A minus C is also a multiple of 4. What does this mean? This means AC belong to the given relation, which implies AC belong to R. So, we proved the given relation is transitive. So, that means the given relation is an equivalence relation. But in this question, we had one more part. What was it? Also find equivalence class 1. So, think of the definition. What do you mean by equivalence class? A set of all x in the original set, which is the original set here, the integers from 0 to 12, such that x is related to 1. So, we will just do the second part, that is we are going to find equivalence class 1. Equivalence class 1 is equal to set of all x such that x is related to 1. So, there is a relation between x and 1. So, we need to select those x satisfying certain condition. So, what was the relation given here? If you take an ordered pair, the difference modulus of, that is modulus of a minus b, it is a multiple of 4. So, we are going to check those x that satisfy this condition. So, how can you modify this? This can be written as set of all x such that its mod a minus b a multiple of 4. So, I can write modulus of x minus 1 is a multiple of 4. So, we are going to select x. So, from where do we select x? In the question it is given x is an integer that lies between 0 and 12. So, we are going to select x, we will substitute here and then we will check which is a multiple of 4. So, let us start with 0. Suppose I substitute 0 here, modulus of 0 minus 1, it is 1. So, we do not say 1 is a multiple of 4. So, we try the next member. So, now the next value that I take is 1. So, if I substitute 1 here, what is it? 1 minus 1, 0. So, I can say 0 is a multiple of 4. So, I got the first x and what is that? It is 1. So, I am going to write equivalence class 1 is equal to the first member that I got is 1. So, it is 1. Now, we check each x in this mode function and we will check whether it is a multiple of 4. So, now let us try 2, 3 etc. And now when we reach 5, look at this, 5 minus 1, it is 4. So, modulus of 4 is 4, it is again a multiple of 4. So, I can include 5. And what is the next value? If I take x is equal to 9, 9 minus 1 is 8 and modulus of 8 is 8. So, 8 is also a multiple of 4. So, I can include 9, x takes the value 9. So, can I select any other value from here? Now, we know 13 minus 1, that is equal to 12, it is a multiple of 4. But here x is up to 12, it cannot accept the value 13. So, we will stop here. So, our equivalence class 1 is equal to set 1, 5 and 9. So, now let us prove the last question in this topic. That is, prove that the relation R on the set n cross n defined by AB related to CD if and only if A plus D is equal to B plus C for all A, B, C, D element of n cross n is an equivalence relation. Also find equivalence class 2, 3. Okay, there are two questions. The first one, we are going to prove the given relation is an equivalence relation, and in the second part we are going to find equivalence class 2, 3. But when compared to the previous questions, here the elements in the set, they are in the form of ordered pair. So, we must be very careful when we prove the equivalence relation. So, anyway, let us start with the first one, that is reflexive. Usually we say let A belong to the set, but our set is n cross n. So, the members in n cross n will be in the form of ordered pairs. So, instead of small a, I will have to use another one, say ordered pair AB. Okay, the members are in the form of ordered pair. So, how do I start? Let AB, this is a single member, let AB belong to our set n cross n. So, instead of writing let A belong to capital A, I would write ordered pair AB belong to n cross n. To prove reflexive, in the definition we prove A comma A belong to the relation. Instead of that, we will have to prove AB is related to AB. We need to prove AB is related to AB. Can we say that? Can we say AB is related to AB. What is the connection here? If AB is related to another pair, then A plus D, that is this member when added to D, A plus D will be equal to B plus C. Okay? So, now we know A plus B is same as B plus A, isn't it? If you add 1 and 2 first and then 2 and 1 both are same. From here I can say AB is related to AB. Yes or no, we will just check. If AB is related to AB, the first is A plus B. So, I got A plus B equal to B plus A. So, I can conclude AB is related to AB, or in other words the given relation is reflexive. Now, let us check whether the given relation is symmetric. For that I need two pairs, symmetric. Let AB related to CD. Earlier in the definition, how did we start? Let AB belong to R, or I would say let A be related to B. Instead of this thing, I am using an ordered pair is related to another ordered pair. The only difference is the elements are ordered pair. Now, what does this mean? This implies A plus D, first element and this element, A plus D is equal to B plus C. From where did we get this? The relation is defined like this. So, A plus D is equal to B plus C, which implies I can write B plus C is equal to A plus D, which implies now B plus C can be written as C plus B. Now, A plus D can be written as D plus A. So, I started with AB related to CD. So, if this relation is symmetric, finally I must get CD is related to AB. Now, let us check from this step, will I be able to write say CD is related to AB. Let us check it. Okay. If CD is related to AB, forget about this step, we'll try this. If CD is related to AB, C plus B, yes, equal to D plus A. So, what we did is correct, and what did we prove? The given relation is symmetric. So, it is reflexive, symmetric, and one more part we need to prove, that is transitive property. Let us see. Now, for this I need to consider two pairs. Earlier it was AB and BC, and children remember here everything is in the form of ordered pair. So, how do I start? Let say some AB, ordered pair AB be related to some CD, and we are ending with CD. So, start with CD and let CD be related to some say EF. Okay? That is how we must select the pair. This is of the form A related to B and B related to some C. We will just write the meaning. What does this imply? This means A plus D equal to B plus C and C plus F, first one and the last one, C plus F is equal to D plus E. Okay. Now, if I name this as 1 and if I name this as 2, I am going to add these two. So, if I add these two, I will get A plus D plus C plus F is equal to, now I am going to add the right side, B plus C plus D plus E. Okay? Addition is over. Now, let us see whether we can cancel something. You have D here, it gets cancelled. What else? C is here, C is here. So, this implies A plus F is equal to B plus E. What does that mean? Does this mean that AB is related to EF? We will check. This implies AB is related to EF. Now, think in the reverse order. First element is A plus F, yes, that is equal to B plus E. So, that means we proved the given relation is transitive, hence this is an equivalence relation. But then do not conclude with this, there was a sub question, and what was that? Also find equivalence class 2, 3. So, how to find equivalence class 2, 3? Equivalence class 2, 3 by definition, that is equal to set of all ordered pair XY such that XY is related to 2, 3. So, children, the only change is equivalence class A. How did we define? Set of all X such that X is related to A. Instead, equivalence class 2, 3 is set of all ordered pair XY such that XY is related to 2, 3. That is equal to. Now, what was the relation? Let us check what was the relation in the question. If AB is related to CD, then A plus D is equal to B plus C. That was a relation. So, now if XY is related to 2, 3, I can write set of all ordered pair XY such that first one is X and the last one is 3. So, X plus 3 will be equal to Y plus 2. Set of all ordered pair XY such that what can we conclude here? X plus 3 is equal to Y plus 2. I can write Y is equal to, if I shift 2 to this side, X plus 1. So, that means I need pairs of this form X comma X, because Y is X plus 1. So, X comma X plus 1, where this X comes from set of all natural numbers. So, what are the members? Give values for X, this is equal to. If I give 1, I get the first pair 1, 2. If I give 2, 2, 3. If I give 3, 3, 4, etc. Okay, it goes. So, that is an equivalence class, that is equivalence class 2, 3, and that was a second subtopic. So, children, let us summarize what we covered in this session. That is, we discussed definition of relation and then different types of relation of that. Empty relation, universal relation comes first, and then we discuss a relation which is very important, that is called equivalence relation. And what is that? A relation which is reflexive, symmetric and transitive is called an equivalence relation. And finally, the small topic, that is equivalence class. Do not forget the definition of equivalence class. For any element A in a set A, equivalence class A is defined as set of all X such that X is related to A, and that relation will be an equivalence relation. So, children, practice lots of questions based on this topic. Thank you.